Hi again, everyone. Now we're going to look at residues with a couple of examples. And just a quick reminder, since this is where we left off basically last time, residue comes from a Laurent expansion around finite number of singular points, right? So we're assuming that we have some region that's analytic except for these finite points. And if it is, we can write a function as a Laurent expansion that is a complex power series about that point, right? And again, we're going around counterclockwise as usual, which means that we are going clockwise around this small contour that captures the singularity. Now, one of the things I showed last time was that the integral of a sub n around z minus z sub 0 to the n d0 is equal to 0 for n not equal to minus 1, essentially because, again, if you look at that integral, it's going to be, there aren't any singularities you have to worry about, right? Anything that blows up, in other words, like a log of z, that kind of pathology. Whereas for n equals minus 1, we have a minus 1 times the integral of z minus c naught to the minus 1 dz, right, is equal to 2 pi I times a minus 1, right? And so we identify that a minus 1 as the residue, and sometimes what we'll denote that as r at z naught. And we were running out of time before I could really fully explain kind of the significance of this, but the residue is what's left over from integrating over this analytic region when you can have a Laurent series. And in fact, if there are multiple singularities, right, then the integral that encloses those singularities of f of z dz is equal to 2 pi I times the sum of those residues. And that's essentially where I left off. I started heading down the road of how you could use this, and now I want to try and justify how you might use this as you head into the problems, and we'll do some more examples in class. So, for example, let's consider the function ez over z minus 1, right? And clearly, I hope, we can ask the question, what is the residue at z equals 1? In other words, we could probably construct a Laurent series based on this function. Now, the trick here is always to figure out what you're going to expand with a Laurent series. So in this case, what we're going to do is expand about z minus 1, right? Make an expansion about z minus 1. So that means that we are going to write this as e times e to the z minus 1 over z minus 1, right? Those are the same. So we can write this as e over z minus 1, and now we can do an expansion of e to the z minus 1. Okay. And that's equal to e over z minus 1 times 1 plus z minus 1 plus and so on. So the expansion itself becomes e to the z minus 1 plus e plus all these other terms. And remember that we're looking for a to the minus a sub minus 1. In this case, it's for z minus 1 to the minus 1. So our residue at 1 in this case is equal to e. Okay. In other words, if you do the contour integral that encapsulates, that covers this singular point, right, what's left over is this residue, and then you can relate that to the entire integral, as we'll see in just a second. Let's look at another example which brings up a really interesting point about all of this. If you think about what the residue actually means and what it looks like, right? We're going to use the fact that you can write r of z naught as the limit as z goes to z naught of z minus z naught times f of z. Okay. In other words, and this is for a simple pole, I should say. In other words, it matters what we're trying to expand about. Right? This goes back to just our definition of what the Laurent expansion looks like and what we're dealing with in terms of the terms themselves. All of the other terms vanish, right? If you imagine you have the Laurent series and you multiply all of it by z minus z naught, right? Now that means as z goes to z naught, everything goes to 0 except for the 1 over z minus z naught term in that limit. So let's look at one example. F of z is equal to, say, z over 2z plus 1 times 5 minus z. And we have, okay, first, where are the singular points? I'll give you a second to think about that. Okay, again, this is kind of tricky. The singular points z naught are minus 1/2 because we have to expand this in terms of z minus that singular point and z equals 5. So what we can ask then is what are the values, what's the residue of 1/2 and what's the residue of 5? Okay, so I'll let you do the residue of 5, but let's see, I'll try the residue of 1/2. So the residue of 1/2 then, if we look at our, so we can use this formula to find the residue. The other way we can find the residue is if we do a Laurent expansion, so we go all the way back up here, right? And we know that a minus 1 is the residue. Okay, but you notice here, it's kind of tricky about what that might mean with the Laurent expansion. So this is another way of getting at it. So in this case, what we would do is look at, again, limit as z goes to, in this case, minus 1/2 of z minus 1/2 times 1/2 z over z plus 1/2. Actually, this should be a plus 1/2, sorry. Times 5 minus z. Okay, again, because we've factored out the 2 here. Okay, so all we're doing is trying to isolate this point, right? So obviously these go away, and we're left with r of minus 1/2 is equal to 1/2 times, let's see, minus 1/2 over 5 minus 1/2, and if I did my math correctly there, minus, that's plus, you should get minus 1 over 22. When you try finding the residue at z naught equals 5, you should find minus 5/11. So try that for fun and profit. Okay. The last example I want to do is how you would use this for integration. So let's, and we're going to do a lot of this on Monday, but let's get a head start on this. So for integration, we might consider how you can do integrals that have these singular points. So one classic is, how do you do the integral of dx over 1 plus x squared? Okay, now this is something that you can actually do with regular methods, but we're going to do this with complex analysis so we can make sure we have the right answer. This is going to be equal to 2 pi I times the sum of the residues. And the way that we're constructing this is assuming that we are in the upper hemispheric plane. In other words, construct our contour and it's clear that we have two singular points, I and minus I, right? And we're going to make this go out to infinity, right? But this captures our pole, okay? We know that there are, just from inspection, simple poles at z equals I and z equals minus I. And we know that we can write 1 over z squared plus 1 is equal to 1 over z plus I times z minus I. Okay. In other words, we're transforming this real integral into essentially the real part of the imaginary of the complex integral. So we have this function. What can we do with it? Let's expand this out. F of z is equal to a sub minus 1 of z minus z naught plus a naught plus the sum of n equals 1 to infinity of z minus z naught n. We can do this just generally, right? Okay. Given that this is where we can do this because we can see that this is where the order stops, so we know that there are no greater terms, that is, there are no terms that are less than minus 1. Right? We could assume that we can expand all of this out, right? But we know that if this is, that this integration is going to be equal to 0. In fact, if we multiply everything by z minus z naught, we get back to that relationship that I showed before, that a minus 1 can be found by z minus z naught times f of z evaluated at, or z minus z naught times f of z. Okay, so we're considering this part of the real plane. So a minus 1 is equal to z minus z naught times f of z evaluated at z equals z naught. That's as the limit goes to z equals I. What that means is the residue at I is equal to 1 over 2I. All we're doing is essentially taking z, oh, this should be I, sorry, z minus I times the function z plus I times z minus I, and getting rid of those poles, and then evaluating this at z equals I. And so that means that the integral from minus infinity to infinity of dx over x squared plus 1 is equal to 2 pi I times the sum of the residues, right, which is 2I, or 1 over 2I, or pi. Okay, so key points here. Residue is what's left over from the analytic region. And you can calculate the residues either by Laurent expansion terms, or by isolation of the singular term, z minus z naught. This is for a simple pole. For higher order poles, we have to take higher order powers of z minus z naught, but for now we're going to focus on simple poles. Now on Monday we'll look at several other integrals, but I hope this gives a little bit more clarity about why we care about residues and where they come from and how you use them. Okay, that's it.